Neha, are you there?
Yes, sir.
So you could start within 5 minutes, or you could start right now because Dr. Tokonami has already joined, so he can join his start his lecture at 10:30.
Okay, sir. Good morning, respected foreign faculty expert, Professor Shinji Tokonami, sir, our course coordinator, Professor Rohit Mehra, sir, and faculty members of the Institute. Dear participants and my colleagues, a warm greeting for the day to all of you. I am Neha Bharti, PhD student of Professor Rohit Mehra, sir. It gives me immense pleasure to welcome you all to the GIAN course on environmental radioactivity monitoring and its impact for health risk assessment, being organized in virtual mode by Professor Rohit Mehra, sir, Department of Physics at Dr. V.R. Ambedkar National Institute of Technology, Jalandhar. First and foremost, let me express our deepest gratitude to the Ministry of Education under the Government of India for initiating the global initiative of academic network GIAN, which fosters academic collaboration by bringing together national and international experts. This program enables the sharing of cutting-edge knowledge and insights, and we are thrilled to contribute to this initiative through today's course. Environmental radioactivity is a subject of critical importance in today's world, with increasing global attention on sustainable development and environmental protection. Understanding the sources, effects, and management of radioactive materials in our environment is more crucial than ever. This course, led by eminent experts in the field, promises to comprehensively explore this vital topic and equip us with valuable knowledge and tools to address related challenges. In this regard, I warmly welcome the coordinator of this GIAN course, Professor Rohit Mehra, sir. Without the efforts of those who helped this course would not have been possible. At present, Professor Rohit Mehra, sir, is working as a Dean Research of Consultancy and Professor in Department of Physics at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar. He has been active researcher in the field of environmental radioactivity for the past 20 years. He has supervised 19 PhD students and currently supervising 6 PhD students. He has published more than 200 research papers in Journal of International Repute. He has been selected among the world's top 2% of scientists by Stanford University and awarded a medal for his research in this field. I invite Professor Rohit Mehra, sir, to inaugurate the course officially, welcome our speaker, and share words of wisdom with our participants.
So good morning, all of you, and I formally welcome Professor Tokonami because he has given his consent whenever we approached him to organize this course. So he has very kindly consented it, and I am very thankful to him because he is always kind to us, to our group also. Because whenever we are doing research since last 20 years, we are doing in collaboration with some of the groups of GNDU, some of the HNB Gadwal University, and even with the Tokonami sir. And we are having some intercomparison activities with the Japanese group also. And I hope that during the tenure of these 5 days, the readers will learn a lot, and we have kept this course in such a fashion that initially Dr. Tokonami will be telling you what are the basics ideas, like how the radon and how the radon isotopes, and they are important for the measurement of environmental radioactivity. And we have designed it in such a fashion that after completion of this course, the participants will learn the basics of environmental radioactivity, the different techniques which are required or used for the measurement of environmental radioactivity, and how it could impact the health risks of the human populations. And I am also thankful to the coordinator of the GIAN, National Coordinator GIAN, my director, my registrar, and along with my team. So who has given me full support for organizing this course. And this is a course, actually, Dr. Tokonami, you might not be knowing the details of this program. The reason is, this is an initiative which has been taken by the government of India to invite some experts in the different areas to deliver lectures either online or offline, so that the human population can get the benefit of their knowledge. So based upon this, people apply for this course, and based upon the biodata of the expert, it has been evaluated by different experts, and your course, this course has been selected. So we are thankful to you that you have given your consent to act as a speaker for this course. Now I would like to hand over the mic to you, and would request you to start your proceedings with the first lecture of on the topic of radon isotope. Welcome, Dr. Tokonami.
Thank you very much, sir, for your kind words. We sincerely appreciate your leadership in bringing this remarkable program. We are particularly privileged to have Professor Shinji Tokonami, sir, our foreign faculty, with us for this course. Professor Tokonami is globally renowned expert in the field of environmental radioactivity, and his presence here adds immense value to our program. Professor Shinji Tokonami is a professor and director at the Institute of Radiation Emergency Medicine at Hirosaki University, Japan. His research primarily concerns radon, nuclear medicine, radionuclides, radiochemistry, and hydrology. His studies on effective dose are significant aspect of his work in nuclear medicine and are often related to studying air pollutants. He has published more over 500 such articles in esteemed international journals and has 4 patents to his name. I invite our esteemed speaker, Professor Shinji Tokonami, sir, to give his introductory remarks.
Thank you very much again. Thank you for a kind introduction. I'm very honored to be here as a lecturer. So actually, this is the second time for me to join the GIAN training course organized by Indian government. So today, first of all, I would like to start the topic on the fundamentals of radon isotopes. Okay, can we start now? So our institute is located by northern part of Japan. It is snowing so much. The snowfall is more than 1 meter. But in the workplace is very comfortable. So now we start the lecture. Can you see my slide?
Yes, sir, we can see, but you can move it.
Okay.
Yeah.
Okay. The first one, the fundamentals of radon isotopes.
Yeah, they are moving, sir. They are moving. Yeah.
Okay, thank you. According to Jacobi, 1993, the saga is a scientific thriller with tragic futures and political confounders. The historical root of this saga reaches back to the 15th century. It is a field full of dilemma, controversies, and frustrations, some of which still persist. What is radon? Radon is an inert and radioactive rare gas. It is natural and is everywhere. It is continually produced by the decay of uranium-238, which occurs naturally in soils and rocks. Radon is colorless, odorless, and tasteless. Needs special equipment to detect radon. Radon generates a chain of radioactive decay products. All of them are heavy metals. There are 3 isotopes of radon. There is a, can you see, wait a moment. Can you see laser? Can you see?
Yes.
Yes, sir.
Okay.
Yes, sir.
Thank you. Yeah. So in uranium-238 series, radon is generated with a half-life of 3.82 days. And finally, it become Lead-206 as a stable isotope, stable element. Here is a uranium-235. Here is a 219 radon, namely actinium. The half-life is very short, less than 4 seconds. So here is a thorium-232. After several decades, the radon-220 is generated. Namely, here is thorium. The half-life is less than 1 minute. The radon-222 is important because it has a long lifetime and it escaped from the rock because it is gas. And long life of Lead-210 becomes a significant background. Radon has a short-lived decay product such as look at this. Polonium-218 with 3 minutes, Lead-214, 27 minutes, Bismuth-214, 19.7 minutes. It is a direct cause of internal exposure due to inhalation. In most cases, thorium is ignored, but in our case, especially Asian countries, we cannot ignore the thorium. Then, exposure to actinium is generally very low. Why is radon of concern? Radon is the second cause of lung cancer, the class 1 carcinogen. Radon is responsible for almost 1/2 of total ionizing radiation doses received by the public each year. The population of lung cancers attributable to radon range from 3 to 14, depending on the average radon concentration in the country. Look at this figure. According to the ANSCIA 2008, the public annual effective dose is a half of the public dose. Effective dose is radon, including thorium, 1.26 millisievert per year. Then terrestrial gamma radiation 0.48 millisievert, cosmic radiation 0.39 millisievert per year. The food is 0.29 millisievert per year. As a total, world average annual effective dose is estimated to be 2.4 millisievert per year. Longer exposure gives a greater risk. Higher levels gives a greater risk. Combination with smoking gives a greater risk as well. This slide shows the behavior of radon progeny in an enclosed space such as a mine or a room. See, radon progenies are solid particles. Some of them are charged. They are chemically active and their half-life is less than 30 minutes. See? Most of polonium-218 freshly formed is positively charged, almost 90%. Rest of them are neutral. After radon decay, solid particles of radon progeny are formed. They are called ultrafine progeny or unattached progeny. Most of them are positively charged, as I mentioned. Radon progeny which attach to ambient aerosols are called attached progeny. Both particles deposit on walls or floors with their own diffusive velocity. The unattached progeny has a higher velocity than attached progeny. Radon in environment. Radon can escape from mineral grains and move into the pores between them. From these pore spaces, radon atoms travel through micro cracks and tunnel volumes either by diffusion or advection. Once radon reaches the surface, it quickly dilutes to harmless concentration. However, its concentration can build up in poorly ventilated areas such as buildings. Regarding radon pathways to homes, radon enters dwellings through both convection and diffusion. Yeah, look at this. Convection and diffusion. Its filtration is driven by the pressure differential between the building shell and the ground around the foundation, produced by the higher temperatures within the shell. It is called the stack effect. Mechanical ventilation, and to some degree also by wind blowing on the building. The primary source of radon is the soil or rock beneath a home. It can enter through the cracks in solid floors, construction joints, cracks in walls below ground, gaps in suspended concrete or timber floor. Here. Gaps around the service pipes. And cavities in walls, like this way. Other sources of radon is the first one, building materials. Brick concrete and gypsum could contain traces of radium and therefore they are potential sources of radon. Radon exhales from building materials to indoor environment. The second source is water. Radon can dissolve and accumulate in groundwater sources such as wells in uranium-rich geological areas. Radon in water can be released into the air during the routine water use. The advection process is considered to be the predominant mechanism compared to diffusion. Here is a radon entry rate expressed in becquerel per cubic meter per hour. Wooden house, concrete house, masonry house, building materials by diffusion is 2 to 16. Subjacent soils by diffusion 4 to 14. Advection 20 to 60. Water degassing almost 1 becquerel per cubic meter per hour. Natural gas, it is around 0.3. Indoor radon concentrations are influenced by soil and geological composition. Radon concentration in soil permeability, building construction, ventilation, weather and climate conditions, and occupant behavior. Radon levels can vary within the building itself as well as can fluctuate daily and seasonally. I can show you the guidelines for safe radon levels. Recommended radon levels. Guidelines typically establish a recommended reference level for radon concentrations in homes. Action levels. The guidelines often specify action levels that indicate when radon testing and mitigations are necessary. Measuring recommendations. Guidelines offer recommendations for radon measurement, including the method and duration of testing. Mitigation measures. If radon levels exceed action level, guidelines outline the necessary steps for mitigation. Public awareness. Guidelines often emphasize the importance of public awareness and education about radon exposure and its health risks. Here is the international and national guidelines on radon gas. This is the authority, county or region, and guidelines. ICRP, International Commission on Radiation Protection, the ICRP recommends that national authorities establish a national reference level that is as low as reasonably achievable in the range of 100 to 300 becquerel per cubic meter, while considering the prevailing economic and societal conditions. World Health Organization. World Health Organization, WHO, recommends a difference level of 100 becquerel per cubic meter for indoor radon. However, if this level is not achievable, they advise that the radon concentration should not exceed 300 becquerel per cubic meter. According to the International Atomic Energy Agency, namely IAEA, in its International Basic Safety Standards, BSS, the IAEA sets a radon reference level of up to 300 becquerel per cubic meter and recommends national policies to establish an action plan for reducing concentrations of radon in existing and new buildings. European Union adopted Directive 2013-59 Euratom, which mandates that member states establish a national reference level for indoor radon not exceeding 300 becquerel per cubic meter. The directive also requires radon risk assessments in workplaces and living spaces, along with mitigation measures for areas with high radon concentrations. In the United States Environmental Protection Agency, EPA, recommends an action level of 148 becquerel per cubic meter for picocurie per liter for indoor radon in homes. If testing reveals radon levels at or above this level, the EPA advises homeowners to take steps to reduce it. In Canada, Health Canada advises that indoor radon levels should not exceed 200 becquerel per cubic meter, recommending mitigation measures if concentrations are above this threshold to reduce levels accordingly. This table shows the indoor radon concentration in several countries. Here's a country, arithmetic mean, geometric mean, and geometric standard deviation. Normally, radon concentration follows log normal distribution. For example, in Canada, the arithmetic mean of radon concentration is 70 becquerel per cubic meter. In Czech Republic, the arithmetic mean is 118 becquerel per cubic meter. In general, the European countries is radon concentrations in European countries is relatively high compared to other countries. Here's Japan. Japan, the arithmetic mean is 14 becquerel per cubic meter. In the case of United States, the 48 becquerel per cubic meter. This data are based on WHO 2019. The radon mitigation is any process or system used to reduce radon concentrations in buildings. Two different general approaches are available for reducing the level of radon indoors. Reducing the rate at which radon enters from its sources. Increasing the rate of removal of radon from indoor air. Before the mitigation, radon level is quite high, but after mitigation, the radon become the low. Radon level is become low. Okay, I found a question, slide 12. How is radon entry rate via different mechanisms is measured? Here, look at this. Yes, actually, they measure the acceleration rate from the mold, or of course, they calculate the radon concentration indoors and in soil. Then they can estimate the radon entry rate. So ceiling foundation cracks and gaps for these techniques are often used as radon mitigation. Applying sealant to cracks and openings in the foundation walls and floors to prevent radon entry. Like this. Look at this photo. And the effectiveness is moderate. It varies depending on severity of cracks. And the cost is low or moderate, between low and moderate. Subslab depressurization. A pipe system is installed beneath the foundation, namely slab, of the building. This system is connected to the fan that continuously draws air and gases from beneath the slab and vents them outside, usually above the root line. The effectiveness of technique is high. Most effective. I can say it is most effective, but the cost is moderate. Here is a depressurization piping system. It's a kind of chimney. Another technique, people use a sub-membrane depressurization, SMD. Similar to SSD, subslab depressurization, sub-membrane depressurization is used when homes have a cooler space instead of a full basement. A plastic sheet or membrane is placed over the entire soil floor of the crawl space. This membrane is tightly sealed to the walls and any supporting structures to prevent radon gas from entering the indoor air. The effectiveness of this technique is high, very effective, but the cost is very high. The ventilation enhanced airflow inside the home to dilute radon levels by opening windows and running exhaust fans. The effectiveness is low, moderate, depending on the ventilation methods. The cost is low. This figure exemplifies the time variation of radon concentration. Well ventilated, this is a closed, the black square means outdoor radon concentration. If the ventilation is worked well, the concentration, indoor concentration reaches outdoor concentration. Despite its negative aspect, such as being a leading cause of lung cancer, radon gas also has positive applications in scientific research and environmental studies. The following properties of radon make it an ideal tracer: short half-life, inertness, high abundance, 2 to 3 orders of magnitude in groundwater than surface water. Sensitivity to sudden changes in subsurface conditions. Positive aspect, here is positive aspect, atmospheric studies, climatic research, tracer for earthquake studies, tracer for geochemical exploration, geochemical and geophysical tracer in marine system. On the other hand, here are negative aspect, health effect, namely lung cancer. Background in laboratories, that is to say, Super Kamiokande Neutrino Observation Laboratory. Radon as an earthquake precursor. Prior to an earthquake, stress builds up in the rocks surrounding a fault. This stress can cause microfracturing or shifts in rock formations, allowing radon to escape more readily from the subsurface. A sudden spike in radon levels has been observed in some cases before an earthquake, leading scientists to consider radon anomalies as potential precursors. Radon monitoring stations have been established in earthquake-prone regions to track fluctuations in radon levels. Variability in soil composition, groundwater movement, and atmospheric conditions can also impact radon levels, making it challenging to distinguish seismic-induced changes from natural variations. Ulmov and Mavashev observed unusual radon concentration levels in hot mineral water from a deep aquifer, 1,300 to 2,400 meters in the Tashkent Artesian Basin prior to the 1966 Tashkent earthquake. Magnitude is 5.3. Other seismic events of magnitude 3 to 4. Analysis conducted after the earthquake showed that radon concentration had peaked several years prior to the main event, returning to normal levels afterward. A similar pattern was observed in the lead-up to large aftershocks, though through over a short-term frame. Here is the first evidence of radon in groundwater as a precursor of earthquake. Regarding Kobe earthquake occurred in Japan, 1995, January 17, magnitude 7.2. The Kobe earthquake of January 17, 1995, magnitude 7.2, which is often taken as an example of the failure of the deterministic forecasting, had been preceded by marked anomalies of radon in water, but since there was no foreshocks activity and the signal was not taken into account, the observation well, located 17 meters deep and 30 kilometers from the epicenter, showed stable radon levels around 20 kilobecquerel per cubic meter at the end of 1993. From October 1994, radon concentrations began to gradually rise, reaching 60 kilobecquerel per cubic meter. On January 7, 1995, 10 days before the earthquake, radon levels spiked sharply, followed a sudden drop on January 10th, just 7 days before the earthquake. The Aquila earthquake, April 9, 2009, magnitude 6.3. It was based on radon measurement by a technician working in the underground laboratory in the Gran Sasso Tunnel. Here is Italy. The main shock occurred 1 week after, Mr. Giuliani had predicted it at with an epicenter located just outside of the city, 55 kilometers away from the Salmona. In the case of radon as an atmospheric tracer, the half-life 3.8 days is short enough, allows tracking over short distances without excessive accumulation. Half-life long enough compared to typical turbulent timescales less than 1 hour. The noble gas does not react chemically with other species. Its only sink is by radioactivity K. The radon is a sensitivity indicator of vertical mixing. Radon's concentration gradient with altitude marks its ideal for studying vertical atmospheric mixing. Global, spatial, and temporal variability. Radon's variable levels globally provide insights into an air movement and pollution patterns. Non-source, the large gradient in the concentrations of radon between oceanic and terrestrial radon sources aid in identifying the sources of air masses, continental versus maritime. Hourly radon time series of typical synoptic scale variability and under conditions of mixed fetch. Observations under persist oceanic fetch as baseline sector. Observation under persistent continental fetch mainland sector. Here's mainland fetch is a clear example of the correlation between the radon concentration and source strength type, continental, island, and marine. Radon as a tracer for monitoring NaPl contamination in groundwater. One of the key properties of radon is that it has high solubility in organic liquid, and hence this property can be utilized for 3 related applications: residual NaPl contamination in soils, residual NaPl contamination in aquifers, monitoring the effectiveness of remediation of dissolved NaPl in groundwater. Soil radon remains trapped within the NaPLs, resulting in a local reduction in the radon concentration within close proximity to the high contaminated area. This graph shows radon activity concentration in the airstream determined during the typical experiment. The arrow indicates the monument of the implementation of the NaPl vessel. Radon as a tracer in the monitoring volcanic activity. There are many active volcanoes in Japan. In particular, the Sakurajima volcano, which is located in southern part of Japan, has been very active since 2009. The phenomenon of increasing outdoor radon-222 concentrations before earthquakes associated with isotopism has been reported by many researchers. Radon exhalation rate from soil surface was measured together with meteorological data in order to discuss the possibility of the prediction of volcanic activity. This here is Sakurajima in southern part of Japan. The picture of Sakurajima. It is still active. This graph shows the number of eruptions in Sakurajima volcano. Here is a number of eruptions and the Western calendar here. The radon exhalation rate showed its maximum value after rainfall. The daily variation of the radon exhalation rate and carbon dioxide concentration in the accumulation chamber seems to be in good agreement. Thus, radon will become a good tracer for carbon dioxide monitoring in environment. It is necessary to develop a correction method for the effect of rainfall on the radon exhalation rate obtained by the flow-through method. I'll explain this technique later. Here is a radon exhalation rate, and you can see the influence of rainfall. This is a precipitation. Here is a carbon dioxide flux. Here is a number of volcanic earthquake. The background radon exhalation rate was 6 plus minus 3 millibecquerel per cubic square meter per second. As a summary, radon is a colorless, the odorless, and tasteless gas which makes it undetectable by human senses. Exposure to radon is the second leading cause of lung cancer, following smoking. The primary source of indoor radon is soil, and it can seep into homes through various entry points such as cracks in foundations, walls, and floors. Despite its harmful effects, radon also has certain applications. As I can say, radon is an visual environmental hazard, but with proper awareness, measurement, and mitigation, its health risks can be minimized. Dr. Mehra, my first lecture is done.
Thank you very much, sir.
Thank you very much, sir. It has been a fascinating talk. If there is any question from the audience, then please ask. Now it's another hour before our following lecture on fundamentals of radon by Professor Shinji Tokonami, sir. Respected sir, I invite you to share your valuable knowledge on fundamentals of radon in continuity with the first lecture.
Hello.
Hello?
Hello. I'm audible, sir?
Yes? Huh?
Hello.
Hello?
Am I audible, sir? Sir, there is a question from one of our participants. Sir, in slide number 2, how is the radon entry rate measured via different mechanisms?
Yes. Yeah, this one.
Yes, sir.
Okay. So, in order to estimate the radon entry rate, we can measure the indoor radon concentration and radon concentration in soil. We can calculate. Also, in some cases, we can measure the acceleration rate, surface acceleration rate. Do you understand what I mean?
Yes, sir. Thank you very much, sir.
Yes.
Sir, there are no more questions from the participants, so we can start our next lecture.
Okay. Maybe we can not fundamental, but this topic is measurement techniques, but it contains many fundamentals. So it takes more time